Hey guys, so we are already to lesson 2.6, which is where we are going to discuss implicit differentiation. And so differentiation means take derivatives, but implicit is explaining or defining a specific kind of function. Okay, so I want to make sure we understand this before we begin. What is the difference between an implicit and an explicit function? So explicit functions are functions where a variable has clearly been solved for or made alone. So like normal equations, I guess, y equals things, x equals equations, anything like these two here. Implicit functions are only implied by an equation, but may be difficult or impossible to solve for a variable. So like this one down here is very obviously complex, and it would be difficult for us to solve this equation for either x or y. Some implicit functions, like this one you see here, it is possible to solve them for y. And just FYI, the way that this one would work, you would subtract x squared, and then you would take the square root. But when you take the square root, you would have to have a plus or a minus. And so what you could do if you wanted to differentiate this implicit function is you could solve it for y and then take the derivative of what you have left. But keep in mind that this plus or minus means that this is actually two equations, positive and a negative version of the same thing. But down at the bottom it says, however, most implicit functions cannot be written explicitly, meaning you can't solve them, most of them, for x or for y, like the one you see down here at the bottom. So that means we have to learn a new technique to figure out how to differentiate things like this. Okay, so some important notation coming up. If I put d dx in front of an equation, it means to take the derivative with respect to x. Okay, take the derivative with respect to x. So let's do that down here for this example. So take the derivative of x to the third with respect to x. Well, that's okay. That's pretty easy because this is in terms of x. So it just means take the derivative, which we would just use the power rule to do that. And I want to point out the reason why this was easy to do is because the statement telling me to take the derivative with respect to x and the fact that the equation had x's in it made it something where our command and our function agreed as far as the variables go. So it had x's in it. I needed to take the derivative with respect to x. So we just did like a normal derivative process. We're going to see something a little bit different with implicit functions. Right, before we get to that, I just want to point out that implicit functions are not actually functions because they don't pass the vertical line test. So if we want to get technical, I need to make that statement to you. So technically, they're just relations. However, functions such as these do come up in nature, engineering, science, things of that along that line. So we can't just ignore them. It is important to differentiate them and kind of study how they move and how the rate of change progresses. So we can't ignore them just because they're complicated or we don't like them. And then I threw in a little dig that you could read down there if you want to. Remember, I was just being sarcastic. Just thought I'd be funny for a second. So let's go through an example. And I'm going to try to clarify the process here for you. So let's say I tell you that y is equal to x squared minus 1. And then I hope we can agree that the derivative of y would be 2x. And I can write the derivative of y as y prime or as dy by dx. Those mean the same thing. Okay, now suppose you were asked to differentiate with respect to x the following: x squared minus 1 to the third power. All right, so let's go ahead and do that. Now I did throw in our new command, our new notation, which means take the derivative with respect to x. So let's go ahead and do this. If I were to take the derivative with respect to x, hopefully you would recognize that you do have a mama and a baby. And so you would have to use chain rule to do this. So you would end up with 3, keep your baby inside, subtract 1 from your power, and then multiply by the derivative of your baby. Okay, and then obviously we would do a little bit of rearranging maybe to make it look a tad bit nicer, but that would be it. Okay, let's try to narrow down what we just did here. So remember how I said let's pretend like y is equal to x squared minus 1, and then the derivative of that would obviously be 2x. Let's compare the stuff in this box to what we got as our answer in the last slide. So if I said that y is equal to x squared minus 1, I could write what I did as d dx of y to the 3rd power. Okay, because y is equal to x squared minus 1. I could then say when I took the derivative of y to the 3rd, or the derivative of this mama baby thing, I ended up getting something like 3 times x squared minus 1. Well, isn't that y? So 3 times y squared. And then what's this 2x deal? Well, 2x, wasn't that the derivative of y? So I could write 2x as y prime. I could also write this as 3y squared dy dx. So all I'm doing is over on the left, I'm taking the derivative with respect to x, and on the right, I'm taking the derivative with respect to x, but using it so that my equation had y's in it. So this is the difference between like an explicit derivative and an implicit derivative. All right. So if I tell you to take the derivative with respect to x, but your equation only has y's in it, your procedure is going to be different than what we just did on the last slide, okay? Because basically that means that you don't really know what your baby is, because you don't know what y is really equal to. So the way this is going to work is you're going to write it as, take the derivative of mama. So mama is y to the 3rd, so that would be 3y squared. And you're going to just make a statement saying that your next move would then be to multiply by the derivative of baby. You're just being abstract in the way that you're writing this because you don't actually know what the baby is, since this is not in terms of x. Okay? The shortcut way of saying this is basically that if you see a command and variables in the equation that don't match or don't agree, you have to do chain rule. And chain rule just simply means make a statement that you would multiply by the derivative of some unknown baby, but you don't know what the baby is, so you're just calling it dy dx. Okay? One other note, all of these things you see here mean the same thing. So I just showed you dy dx times y, of y to the 3rd. That could also be the same exact procedure if this was called f of x. Those are the equal. Or if I just call it unknown baby. Those are all equivalent statements. All right, let's do 2 examples. So the first one is a sum, which means I can just split this up and look at one thing at a time. So I'm going to look at the derivative of x, and then I'm going to take the derivative of 3y, and I'm just going to add those answers together. Okay, so here in this first part, my command and my variable agree. So I'm making a little note that my variables agree. So I can just do a regular old derivative here. So what is the derivative of x? The derivative of x is 1. Okay? In the second part of my question, my command says take the derivative with respect to x, but my equation has y's in it. So my variables do not agree. When this happens, you have to use chain rule, which means you're going to have a dy dx as part of your derivative to basically say that you understand that you need to also take the derivative of baby. Now, when you do this, you're going to start by saying 3y is your mama, and you got to start with taking derivative of mama. So what's the derivative of 3y? Well, that would just be 3. And you are going to multiply by the derivative of baby, which you don't know what your baby is, so you're just calling it dy dx. And that would be as much as you could do there. Okay, the second example, I can't split it up like I did in the first one because I don't have a sum or a difference. This one is multiplication. So we are going to have to use product rule to solve and find this derivative. Okay, to use product rule, I think it's helpful if we start by saying that u is x and v would be x squared. And I think I'm even going to kind of map this out by writing down all my information that I need. So in product rule, it was u prime v plus u v prime. So I'm going to write down what u is, I'm going to write down what v is, and I'm going to write down u prime and v prime. U prime would be 1. I would just do a regular derivative there because it's the command and the variable agree. But when I go to do v prime, since it has y's in it, I'm going to have to use chain rule. So derivative would be 2y, but then multiply by dy dx to say that you don't know what your baby is and you have to multiply by the derivative of baby. All right, now let's take all of this and let's put it into our product rule. So u prime times v would be 1 times y squared plus u times v prime would be x times 2y dy dx. And then I suppose you could clean it up a little bit and just make it y squared plus, I don't know, maybe 2xy dy dx. But that's essentially it. Okay, I put down like a step-by-step process here for you to go refer back to later if you want to. Let's just get to an example. So example A, if x squared plus y squared equals 25, find the derivative. This is an implicit function because it's not solved for any variable. So we're going to just do implicit differentiation for this. So I'm going to take the derivative with respect to x of everything I see, and that means both sides of the equation. I don't have any product rule or quotient rule to worry about, so that's good. All I need to worry about is do my variables agree or not. So I'm going to look at each step along the way. And I do have sums, like a plus and minus or plus signs all through this problem, so I can actually take the derivative of one piece at a time and then just kind of put it all back together. So I am going to show that that's what I'm doing by writing d dx in front of each component. Not really a necessary step, but since we're taking notes, I thought I'd show you what that looks like. Okay, so for the first one, my variables agree, so I can just do a regular derivative. So derivative of x squared is 2x. Second part, my variables do not agree, so that means that there's a baby in here that's not shown. So we're going to do chain rule. Derivative of mama would be 2y. Derivative of baby would just be called either y prime or dy dx, so we have to have that there. The third part doesn't have variables, like 25 is just a constant, which is totally fine because the derivative of any constant is just 0, so 0 for that part. Now, we haven't had an equation like this one yet, so I'm going to show you what to do from here. From here, your job is to find the derivative, and the derivative is represented by dy dx. So you're actually going to solve this equation for dy dx. So that means that first you're going to subtract 2x, and you're going to divide by 2y. So I would have negative 2x over 2y, which you could reduce down to negative x over y. And in implicit differentiation, your answer will often have x's and y's in it, which is totally normal. So this is a perfectly acceptable answer. Let's go to part B now. So part B says find an equation of the tangent line to the circle at the point 3, 4. Well, we have the derivative of that circle is negative x over y. So all you're going to have to do is plug in 3 and 4 to your derivative function, and that'll tell you the slope there. So x is 3, y is 4. So the derivative is negative 3/4, which means your slope is negative 3/4. Okay? And then you guys, you know how to find equations of tangent lines. We've done it so many times at this point. Now you're just going to do point slope form and plug in your y, which was 4, and your x, which was 3, as well as your slope, and get y alone. So you would get, let's see, negative 3/4 x plus 9 over 4. And then if you add 4, you would get, what, 25 over 4. Oops, I forgot my x. There we go. Okay, I think I just have maybe one or two more to go over. Example 2, find the derivative given that this is my function. Okay, I can't solve it for y. I could maybe solve it for x, but it would be really messy. So let's just use implicit differentiation so that we don't have to worry about all that. So we're going to take the derivative with respect to x, because that's what it says to do here. So we got to check and see if our variables agree each step along the way. So I'm going to look at y to the third first. My variables do not agree, so I need to do chain rule. So that means I would have derivative of mama is 3y squared times dy dx to represent the derivative of baby. Okay, go to y squared. Again, our variables don't agree, so we're going to do derivative of mama times derivative of baby. Go to the next step, negative 5y. Again, variables don't agree, so take the derivative of negative 5y and you get negative 5. You need a dy dx since you don't know what your baby is. When you get to the fourth step, negative x squared, our variables do agree. And when your variables do agree, you just take the regular old derivative and you don't need anything else. So negative 2x for that part. And then at the very end, you just have a constant value, and the derivative of a constant value is 0. So now we have this big old mess, and our job is to find dy dx. So what we're going to do is we're going to take any terms that don't have dy dx in them and add it or move it over to the other side. And then, actually, I'm going to skip a step. What we would do then with the remaining terms is we would factor a dy dx out. So all three remaining terms have a dy dx. I'm going to factor that out like this. And then to solve for dy dx, all you would need to do at this point would be to divide by everything that's in this parentheses. So we're just going to keep it all together and write it as 2x divided by 3y squared plus 2y minus 5. And so that fraction would represent the derivative, which means the slope of the tangent line. Okay, let me show you. I'm going to skip example 3. This one does have a quotient rule situation, so you would have to do that for the right side. But you can look at the PDF of the notes to get this one. Let's go to this last example, number 4. So find y prime, which means find dy dx for this equation. And obviously it is an implicit equation because I've got x's and y's all over the place. So we're going to find dy dx for both sides. All right. This problem has a lot happening because there's on the left side a mama baby, on the right side I have a product rule, so here we go. Okay, so the first part says take the derivative with respect to x, and then we have a mama baby. Well, mama is sine, which, whoops, not sine. The derivative of sine would be cosine. Keep your baby. And then when we go to take the derivative of the baby, the derivative of x is 1, but the derivative of y, since that variable doesn't agree with the command, you would do 1 times dy dx. So the 1 represents the derivative of y, and the dy dx represents the fact that your variables don't agree and you need to multiply by derivative of baby. On the right side, you have a product rule situation. So you're going to have u and v, and you're going to do u prime v plus uv prime. U prime v plus uv prime for product rule. U prime is asking you to take the derivative of y squared, and that the variables do not agree. So you would have to do 2y dy dx for the u prime component times v plus, I'm going to write it down here, u v prime. Now when you do v prime, you're just finding the derivative of cos, which the variables do agree there, so that would just be negative sine. And on this one, there's not a whole lot we can do to make it look nicer, so we could just stop right there.